Hello everyone, this is chapter 9.4 where we'll be discussing partial fractions, otherwise known as partial fraction decomposition. And you'll kind of see why the word decomposition is brought up. But for right now, let's just recall this. So we have these two rational functions, so basically a polynomial over another polynomial, and we can combine them because in this case we're subtracting, but usually we'll be adding, but it doesn't really matter. Adding and subtracting is kind of the same thing. So to do that, I'm going to multiply top and bottom by the opposite denominator. So here I'm going to multiply top and bottom by x plus 2. And this I'm going to multiply top and bottom by, of course, x minus 3. And what we end up getting is, well, let's see. So I forgot a parenthesis there. That's fine. So we end up getting is 3 times the quantity x minus 3 minus 2 times the quantity x plus 2 all over the common denominator, x plus 2 times x minus 3. And what you'll notice is that, well, you can of course FOIL the bottom to get x squared minus x minus 6. Good. And in the numerator, this is 3x minus 9. And if you distribute the negative 2, you get negative 2x minus 4. So those actually combine. I'm going to skip writing it out, so I'll actually jump to the combination, but I'll say it out loud anyways. 3x minus 2x is just x. Negative 9 minus 4 is negative 13. So this is what we end up with. So we're going from this subtraction to this. So the kind of conclusion is that this fraction decomposes as this addition of two, I want to say smaller rational functions. Now when I say smaller, I really mean that their degrees are smaller. Here the degree is 2, here the degrees are 1. So how do we do this? So this process, by the way, is decomposition. It decomposes. So we have this decomposition of a rational function into two other rational functions where the denominators have smaller degree. So we're basically undoing this process. And the question is, how do we do that in general? As it turns out, there's a few cases, and we'll kind of see why this is in chapter 9, because so far it seems unrelated to everything we've been seeing so far in chapter 9. But I'm just going to show you right off the bat. Here's what we're going to do. The first thing we want to do is we want to notice here, these are indeed these two that multiply to this. So right away to get that, I'm going to factor the denominator. So the first thing I want to do is I want to throw this away and I'm going to factor the denominator. So let me erase. In this case, it says x4 plus 5x plus 4, and that of course factors as x plus 4 times x plus 1. So allow me to erase to get that. X plus 4 times x plus 1. And now what I want to do is I want to write this, I want to decompose this as something over x plus 4 plus something over x plus 1. Good. Now, those somethings I'm going to call A and B. You can honestly call them whatever you want. You don't even have to use capital letters, but that's just the traditional notation for partial fraction decomposition. Okay, good. So now what? Well, now we can actually follow this process to see if we can relate the new numerator combining these two with A and B to this original numerator 1. So notice we're going to apply the same thing we did here. I'm going to multiply top and bottom by x plus 1 for this fraction, and multiply top and bottom by x plus 4 for the second fraction. So really we're kind of just multiplying the numerators by opposite denominators, but it depends in general because you may have more than two factors, meaning you'll have more than two fractions adding together. So it kind of depends in general. But in this case we get this. We get a times the quantity x plus 1 plus b times the quantity x plus 4 all over the same common denominator, which is of course x plus 4 times x plus 1. And notice so far, the denominators are indeed the same, so that must mean, since we want these fractions to be the same, that means that the numerators must be the same. So what we get from this is the following equation. We get a times the quantity x plus 1 plus b times the quantity x plus 4 is equal to the original numerator 1. Good. Now that we've arrived here at this main equation, there are honestly a few ways of doing this, but the best way to do it at this level to relate to chapter 9 is to do what is called equating coefficients. So I'm going to so-call equate coefficients. So really what I want to do is I want to notice that a and b are just numbers, they're constants that we're going to solve for. So I'm going to expand this out a little bit by distributing and then combine some terms. So notice here I get a times x is ax and b times x is bx. So in fact, let me just do it. So we have ax plus a plus bx plus 4b is equal to 1. Let me kind of separate this. Okay. So now notice the x is combined to a plus b times x, and the constants kind of combine to a plus 4b. So they don't really combine, but what we're doing is we're just kind of grouping them together so that we have a number times x plus a number. And I want to write the other side as such as well. So this 1 we can actually write as 0 times x plus 1. Now why are we doing that? We're doing that to equate the coefficients. So the coefficient of x here is equal to the coefficient of x here. The constant here must be equal to the constant there. It's a little bit of a weird thing to do, but honestly, this is kind of one of the methods. I'll show you the other method a little later, but for right now, in fact, maybe I'll show you the other method right after this. But for right now, let's continue. So what we get really is a system of equations. I don't have too much space, but I think we're okay. So for the x coefficient, we have the equation a plus b is equal to 0. And for the constant coefficient, or constant equation, we have a plus 4b is equal to the constant 1. So notice this is just a system of equations that we can solve. And in fact, we can solve this by elimination. Let me multiply the top by -1. So when you add straight down, you get that the a's cancel. And really we're doing 4b minus b because of the distribution there of negative. So this becomes 3b is equal to 1. And that tells me that b is equal to 1/3. Also notice that a plus b is 0. So if you plug this back in, a plus 1/3 is 0. So that means a is negative 1/3. So this implies that a is negative 1/3. And that's it. We're kind of done. What do I mean by kind of done? I mean that we have decomposed this now as the following. 1/3, I guess negative 1/3 for a over x plus 4, plus for b, positive 1/3 over, what was b over? B was over x plus 1, so that'll be over x plus 1. And this is our partial fraction decomposition of the original rational expression here. Good. So I'm going to erase a few things. I'll just erase the above part actually, and I'm going to not redo this, but I'm going to redo it from this point. And instead of using the method of equating coefficients, I'll show you something a little different, and then we'll go from there. Right, so now we enter what is called Heavyside's method. Heavyside, by the way, was the mathematician, so this is someone's actual last name. So what we're going to do here is we're going to actually basically do the same process up to this point for this equation, which is why I circled it. So I'm going to start back here. So for the same previous example, we have this equation, a times x plus 1 plus b times x plus 4 is equal to 1. And what Heavyside basically says is that you can let x be whatever you want, and then you'll get a new equation. So for example, if we let x equal 2, we get 3a, and that would be 6b. So it's 3a plus 6b is equal to 1, and that would be an equation. We can plug in another value of x, get another equation, and then we can solve that system of equations, much like we did here, solve this system. But this is where it gets really sweet. We can plug in anything we want for x in this equation, and it'll hold. We'll get a new equation involving a and b. So why not just plug things that'll make stuff go to 0? So here, if x is -1, notice we'll just get a times 0 plus b times -1 plus 4 is 3 equals 1. That means 3b is 1. So look at that. Right away we get b is equal to 1/3, which kind of took us a little bit of time to discover here. So the reason why I don't quite like showing this right now at this level is because it kind of goes away from why this section is placed in 9.4, because really it was supposed to be an application of solving a system of equations. Now, The other thing is that we'll kind of see more setups and more situations of partial fractions later on in this video. Even using Heavyside's method, sometimes you can't escape the fact that you have to solve a system of equations. So regardless if we introduce Heavyside's method or not, there's really no way around solving a system. But in this case, we don't actually have to. Because now if we plug in, let's say, -4, which will make x plus 4 0, well, now we get -4 plus 1, which is, let's see, -4 plus 1 is -3, so that's a times -3, plus b times 0 is equal to 1. That gives us a -3a is equal to 1. So dividing by -3, that gives us a is equal to -1/3, and we're home free. And by the way, you can always check your answer by running the same, the same argument. In other words, you can combine this back into one fraction with the same common denominator, and you'll see indeed the numerator will combine into just 1 in this case. Right, so now I want to decompose this particular rational expression. And what I'm first going to notice, remember, is that we want to factor the denominator. That's how we always get the ball rolling. So here I'm going to notice they all have x in common. So if you pull out an x, you get x squared plus 2x plus 1. And we know actually how to factor x squared plus 2x plus 1. It's just x plus 1 times x plus 1. And there's kind of a little bit of an issue here. And the issue is that if you kind of take what I said as fact from the previous example, then this would decompose as a over x plus b over x plus 1 plus b over x plus 1. But there's a problem. And the problem is that, sorry, this should be c over x plus 1 is what I meant to say. And there's a problem. What's the problem? The problem is that b and c are just constants. So notice they have the same common denominator. So in reality, we can write this as b plus c over x plus 1. And b plus c is just some other constant, and you can relabel it as b, for instance. So in fact, this setup would be the same as just this setup. And that doesn't really do us any good, because notice when you combine these, your common denominator will just be x squared plus x, not this cubic actually. So in other words, not only do we need x plus 1 involved, but we actually need x plus 1 all squared involved. So this is what happens when you have what are called non-distinct factors, when you have a repeated factor, in other words. When you have a repeated factor, you need to include it up to its power and all other powers below that. So in this case, it's repeated twice, so we need 1 for the first power and then 1 for the second power as well. Similarly, if it was x plus 1 times x plus 1 times another x plus 1, once we factored the original denominator, then you would need x plus 1, b over x plus 1, c over x plus 1 squared, and then you would even need, I guess, capital D over x plus 1 all cubed. And we'll summarize that at the very end. So now what? Well, now we have a pretty crazy thing going on, and we can try to get things going kind of like we did in the previous example. I'm going to try to finesse this a little kind of quicker though. So I notice that I'm going to basically get this in the end. I need to multiply this top and bottom by x plus 1 quantity squared to get this common denominator, because that's really what this is. So I'm going to have to multiply a on the top by x plus 1 quantity squared. Here, this needs an x plus 1, but it also needs an x to make this common denominator. So b is going to get a hit of x and an x plus 1, but only one x plus 1 because it already has one in the denominator. C only needs x in its denominator, so it's cx like that. Great. And what we saw from the previous example is that this new numerator, once we have the denominators matched, which we do now, would be equal to the original numerator. So what we have now is that a times the quantity x plus 1 squared plus bx times x plus 1 plus cx is equal to this, which is 3x squared plus 5x plus 3. All right, so now if you want to expand it out and find a system of 3 equations, that's fine, you can do that. In fact, I encourage everyone to try to do that to see if you get the same thing I'm going to get right now. But what I'm going to do instead, of course, is use Heavyside's method as much as I can. So I'm going to let x equal 0 because we have a 0 right here and here. So letting x equal 0, we'll cancel these two. 0 plus 1 is 1, squared is 1, so we'll just get a on the left. On the right, plugging in 0 just leaves us with 3. So right away we get a solution, which kind of just goes to show how powerful Heavyside's method is. It's a very simple concept too. Now I'm going to plug in -1, which of course will give me a 0 here and here. So those two are gone, and now we have c times x, which is -1. So that's a negative c on the left. On the right, -1 squared is +1, so that's 3. -1 times x is -5, and then plus 3. So notice that's just 6 plus 5. So altogether we get negative c is equal to 1. Dividing by negative gives us c is equal to -1. Great. And now we're kind of stuck, because we don't have any other value for x that'll give us 0. But the good news is that we know what a and c are, so now all we need to do is find b, and Heavyside's method doesn't say just to plug in what gives you 0, it says you can plug in any value for x. So in fact, let's plug in the next best thing, let's plug in 1, any nice number really, and now what we'll get is the following. We'll get a, which we know is 3 now, times, well, 1 plus 1 is 2, squared will give you 4, plus b, which we don't know, times x, which is 1, times 1 plus 1 is 2, so that's 2b, plus c, which we know is actually -1, times x, which we're replacing with 1, equals, when you plug in 1 for x here on the right, you get 3 plus 5 plus 3, which is 6 plus 5, which is 11. So let's combine some things here. We get 12 plus 2b minus 1 equals 11. Notice these combine to 11, so you can actually subtract 11 to both sides. And you just get that 2b is 0. Dividing by 2 gives you b is 0, actually. Nice. So what that says now is that we actually know the decomposition of this original guy here. It's 3 over x plus 0 over that, so we really don't need it, and -1 over this. So I'm trying to find a space where I can put our answer. I guess I'll just write it over here. So altogether our answer is this, 3 over x plus -1, so let me write it as -1 over x plus 1 squared. So as it turns out, in this particular case, we didn't quite need the x plus 1 to the first power, but in general, when you have a repeated factor, you do need all lower powers up to how many times it repeats as a factor. So in this case, it repeated twice, or there's 2 instances of it anyways. So the highest power of that will be 2, and you need all lower powers as well. But in this case, like I said, b coincidentally was 0. All right, good. So now we're going to take a look at even one more type. In fact, there's a few more types. We're going to take a look at more types of examples where we have different setups, essentially, for partial fraction decomposition, much like this was a different setup than what we had previously. Right, so this example is a little unusual. Notice we can factor the bottom. Again, you always start off by factoring the bottom. And we'll get x times the quantity x squared plus 4. Now, what makes this unusual, of course, is that that's the furthest we can go. Notice if it was x squared minus 4, we can use difference of squares and get x minus 2 times x plus 2. But x squared plus a number is never factorable. And we've seen that before because if it were factorable, it would have a real 0. But if you set this equal to 0, in this case, you would get x squared is equal to -4, which would actually give you an imaginary solution. X is equal to plus or minus 2i, which is not good. It's not real. So with that being said, this is not factorable over the real numbers. So this is the furthest we can go. So what this tells us, more than likely this decomposes as something over one of the factors plus something over the other factor. Just kind of logically doing what we did before. Notice the previous example we saw showed a different type of setup, but we had a repeated factor. Here there's no repeated factor, but the only real difference is that one of the factors is quadratic. This is known as a quadratic irreducible, or I guess irreducible quadratic. It's a quadratic factor that can't be factored, as it turns out. Now, the I guess big takeaway here is that you can try to make this work out, but it's not really going to work. In fact, the reason why it doesn't work here is because here, in our numerator, we have 3 coefficients. We have a constant, we have a linear, and we have a quadratic coefficient. Here, we only have two constants that we're trying to find, a and b. And basically, if you actually try to equate coefficients, you'll get a weird system of equations that won't actually work out, and it will actually have no solutions. And the reason being is because here we'll have a possible for 3 equations, but only 2 variables, not 3 variables. So in fact, long story short, the setup you should use when you have an irreducible quadratic as one of your factors in the original denominator is that the numerator of that fraction with that irreducible quadratic must be linear. So the big takeaway here is that whatever your denominator is, the numerator must have degree 1 less than that. So notice here the highest power of x is 1, here the highest power of x is 0. Here the highest power of x is 2, here the highest power of x is 1. Okay. Now again, that's not including the the exception to that, of course, is with the repeated factors, because something like x plus 1 all squared, like we saw in the previous example, technically has degree 2, but I'm not considering that when I'm doing this setup. So for this setup, it's only when your denominator is a quadratic that can't be factored. So kind of keep that in mind. So really, we've seen 3 setups so far. So now let's actually solve this out. I'm going to multiply a by x squared plus 4. I'm going to multiply bx plus c by x. This is going to be all over the common denominator, x times the quantity x squared plus 4, which is, of course, the original denominator, just factored. And that means this must be equal to the original numerator. So we have this equation, a times x squared plus 4 plus x times bx plus c is equal to 3x squared plus 4x plus 4. So let's see if Heavyside's method comes to the rescue here. That's 4x plus 4, sorry. Okay, good. So now notice the only real 0 we have is where this is 0, and that's x equals 0 itself. And that'll give us something. It won't give us enough, though, as it turns out. So when x is 0, that's gone. When x is 0, this is 4a on the left. On the right, all of those are 0 except for 4. Dividing by 4 gives you a is 1. Perfect. But we still have b and c to solve for. And notice, these are never 0. Well, this is never 0. This is 0 when x is equal to c over b. But we don't, or negative c over b anyways. But we don't know what c and b are, so that's useless. So really, I'm looking when the denominators are 0 and plugging those in for Heavyside's method. But remember, here that would be plus or minus 2i. And I don't want to get complex numbers involved. That seems like too much. So what I'll do is I'll just do what I did previously. I'll just pick any numbers I like and use the fact that we already know what a is, and then we'll get a nice equation for, well, b and c. So in this scenario, we have no way to avoid systems of equations. So let's see how that pans out. So when x is 1, we have 1 for a times 1 squared plus 4, which is 5. Good. Plus 1. And then here, 1 times b is b, plus c is just b plus c. Great. We plug in 1 here, we'll get 3 plus 4 plus 4, which is, I guess, 11. So in total, we get 5 plus, let me write it over here, I guess. 5 plus b plus c is equal to 11. If you subtract 5, you'll get that b plus c is 6. Great. So that's one equation. And we're going to make a system out of this. So now to get our next equation, we can let x be anything else. If you want to use 2, we can use 2. We just can't use what we've already used, or else we'll get the same result. So I'm actually going to use negative 1. So notice, negative 1 squared is still going to give me 1 plus 4, which is still 5. So this will still be 1 times 5. That's okay. Plus, now this is going to be negative 1 times negative b plus c equals negative 1 squared is positive 1 times 3 is 3. And then 4 times negative 1 is negative 4, so I guess I'll write minus 4. And then plus 4, notice these cancel out. So let's see what we have. We have 5 minus, let me write it as, I guess I'll write it as negative b plus c, that's fine, equals 3. If we subtract 5 to the other side, like this, we end up with negative b plus c is equal to negative 2. I guess negative 2. We could... You know what, that's fine. I was going to say we could divide by negative, but I'll just distribute this. So what this really amounts to is the following. It's b minus c is equal to negative 2. And that's our other equation in the system we want to set up. So now allow me to erase this to clean things up a bit. Alright, so now I'm going to use these two equations we just got as our last result, solve the system involving those two. Notice if you add straight down right away, this is actually a really nice system to solve for. The c's cancel, so we get 2b, b plus b is 2b after all, is equal to 4. Dividing by 2 gives us a b is equal to 2. Perfect. But now what's c? Plug it back into the original first one. 2 plus c is equal to 6. Subtracting 2 gives us a c is equal to 4. Perfect. So now finally we're done. We can just plug a, b, and c back into our original theme. And that's kind of the other funny thing about these types of problems. Your setup is your answer. We just go through all this work to find out the actual components to the answer. So now finally our decomposition is 1 over x plus bx plus c, so it's going to be 2x plus 4, all over x squared plus 4. And you can actually verify this again by combining these two fractions together and see that you indeed get the original fraction. Right, so this example is a little different in the sense that there's no real new setup, but the real difference here is that the numerator is larger, the degree anyways, is larger than the denominator. And we actually haven't quite seen that before. And in fact, kind of think about it. If we were to set this up, notice the denominator factors as x plus 1 times x plus 2. If we were to try to force the setup like usual, we get this, which will not make any sense because remember a and b are constants here. They're not variables. So if we combine, the degree on the top will just be 1. Because here we would get a times x, here we would get b times x when you multiply, and that would just multiply and combine to a number times x. We don't even get x squared, let alone x cubed. So when your numerator is the same degree or higher than the denominator, you have to use polynomial division. So I'm going to use polynomial long division in this case, and let's see what we get. So I'm going to divide the denominator, x squared plus 3x plus 2, into the numerator, 2x cubed minus x squared plus x, and then plus 5. So let's see if we remember how this goes. We're going to look at the front ones, the two leading terms, multiply this by whatever we need to match this one on the inside. That's 2x in this case. Multiply each of them by 2x. We get 2x to the third. We get 6x squared. We get 4x. Then we're going to change the signs of the terms because we want to subtract. That. When you add straight down, the first two, of course, cancel by design. We end up with negative 7x squared. Here we get, let's see, I guess negative 3x. Bringing down the 5 gives us 5. And now comparing the two leading terms, we need to multiply this by negative 7. And we get, let's see, negative 7x squared. That's going to be negative 21x. That's going to be negative 14. And then I want to subtract again, so I'm going to change the signs. In this case, I'll change to positive. These cancel out, and we end up with, let's see, that's 18x, and then that's plus, well, I guess plus 19, isn't it? Okay, good. So that means we've rewritten this side here. But so before even getting into this partial fraction decomposition setup, we've rewritten this side here as our quotient 2x minus 7 plus the remainder 18x plus 19 over the original denominator, which we know factors as x plus 1 times x plus 2. So now what we're going to do is we're going to use our partial fraction decomposition methods on the fraction part. So again, notice that we left off with this, so now we're going to decompose what we have left over to this fraction. And since the denominator factors into two distinct linear factors, we can actually decompose it as a over x plus 1 plus b over x plus 2. If we combine these into one by multiplying by opposite denominators, we get this equation, a times x plus 2 plus b times x plus 1, as the numerator is equal to the original numerator, 18x plus 19, And now using Heavyside's method, we can plug in x such that one of these factors is 0, when x is negative 2. On this side we get negative 36 plus 19, which is negative 17, equals, that goes to 0, that'll be negative b. So dividing by negative 1 gives us a b is positive 17, great. When x is negative 1 on the other hand, that'll make this negative 18 plus 19, which is 1, equals negative 1 plus 2 is 1 times a is just a, and that goes to 0, so we're left with this. And that means that we're done basically. So our final partial fraction decomposition is just 2x minus 7 plus this fraction, which decomposes as 1 over x plus 1, plus b, which is 17 now, over x plus 2. Perfect. And now we're going to see one last example of something a little different before I summarize and conclude 9.4. Right, so now for this last example before we summarize things, well, let's just kind of check to see how we would begin. And honestly, we have all the tools necessary to begin decomposing this, or at least the setup for decomposition. And we don't have to do anything crazy like polynomial division like we did for the previous example, because the degree on top is smaller than the degree on the bottom for sure. In fact, the degree on the bottom, once you expand out, is going to be 2 times 2 plus 3, which is 7. If you expand it out, you'll see what I mean. And the degree on top, of course, is 1. So what I'm going to do is I'm going to notice, first off, this is already completely factored. We have a repeated factor here. We have a repeated factor here. And this one that's repeated is actually a quadratic irreducible quadratic. So for x cubed, I'm going to write a over x plus b over x squared plus c over x cubed, because it goes all the way up to the largest power present in that repeated factor, which in this case is 3. Perfect. And now on to the next factor, x squared plus 1. Recall that for the irreducible quadratic x squared plus something, its numerator must be something times x plus something. We're at a, b, c, d, so it's going to be dx plus e, I guess. And then plus, since it's repeated now, we need another one for another term here for this factor squared. So x squared plus 1, quantity squared, and its numerator is going to be another linear term, linear expression, which now we're at f, so it's going to be fx plus g, I guess. Yikes. So it's a lot going on. Obviously, there's a total of 8 different things we would have to solve for, or I guess 7. 7 different things we'd have to solve for here. And yeah, we're not going to do it actually. I just wanted to show the setup. This is way too much. I think it'll take way too long, and I don't want the video to be that long. If you're daring enough, you can definitely try it on your own. It's going to be pretty complicated though, because notice, even by Heavyside's method, only x is 0 is a 0 of the denominator. So that doesn't even give us much. In fact, we would basically we'd be forced into a situation where we would have a system of basically, let me see if we can even, we'd have a system of like 6 or 7 variables, which I don't want to do. But in fact, if you do try to do it, you'll notice there'll be a lot of holes in the system, so it's not a very full system. So it's doable, but not a chance. I'm not going to do that. So just, again, so that the video is not super long. So right now I'm just showing at least the setup. And now I want to summarize what we've learned so far in 9.4. So now finally is a summary of all of the setups we've seen so far, and there are 4 of them. One where we have distinct linear factors, where each term would be a constant over each factor. Linear, by the way, is of the form ax plus b. We really saw things like x plus 1, x minus 3, stuff like that. But it could technically be like 2x plus 1, for instance. Repeated linear factors, where the linear factor would repeat a few times in the factorization of the denominator. We would need a over that factor plus b over that factor squared, all the way up to however many times it repeats. So if we only repeated so that there's 2 of them, we would stop here. But if there were 3 of them, then it would be a over this one plus b over it squared plus c over that to the 3rd power. And in fact, in the last example we saw, we had x, which is technically a linear factor, to the 3rd. So that's why we needed a over x plus b over x squared plus c over x cubed. 3 is where we had irreducible quadratic factors, where the numerators must be linear, so ax plus b over that irreducible quadratic factor. And 4, if you have a repeated quadratic factor, irreducible quadratic factor, it's a combination of these two. And you can clearly see we need a linear numerator for each one, where A, B, and C, all these capital letters, are unknowns to be solved by either Heavyside's method or equating coefficients to get a linear system. You can do it that way. And again, you repeat it up to however many times it repeats. So the largest amount of times it's repeated. And then finally, I have to say here below, it's not really a setup, but it's something you kind of need sometimes. If the degree of the numerator is greater than or equal to the degree of the denominator, you must use polynomial division, and then use either of these setups depending. Because after you use this division, you'll have a polynomial plus another fraction where the degree is basically the remainder of that division. In other words, it'll be the polynomial will have a smaller degree on top than it will on the bottom, and then these setups are applicable. Great. So 9.4 is a little bit of a doozy, but it was definitely a good application of linear systems and a fantastic subject that you'll actually see come to bite us again for calculus and even for differential equations if we get that far. And yeah, that's all I need to say there, and I'll see you in the next video. Thanks for watching. See you then.